Just like that. Okay. My name's Jim Starkey, that's what the slide says. This actually isn't the users conference. Probably most of you have noticed that. This is basically the same talk, and I know some of you were there, that I gave there with a couple differences. One is I'm not nearly so constrained for time. Second is Martin Mikos isn't sitting here in the audience, or if he is, I haven't noticed him. And third, to the best of my knowledge, I don't have an Oracle Vice President sitting here taking good notes. Before I start, I would like to introduce Ann Harrison, who is also part of the K-band development office of MySQL. Ann is also my wife, co-conspirator. She's actually working for MySQL half-time, and interestingly enough, she's working for the Firebird database half-time. So, and even more interesting, she is the only female engineer on each of the projects, which is something that intrigues me. Anyway, tonight, I'm going to be talking about Falcon, which is a new storage engine. If you have a burning question, by all means, put your hands up, and we can take it then, or there's certainly room for questions at the end. There's a missing R in there, isn't there? I haven't noticed that. It's introducing. Anyway. Okay. First, what is Falcon? It's a transactional MySQL storage engine. It's part of the pluggable storage engine architecture for the MySQL server. It plugs in, it's transactional. It's based on the NetFrastructure database engine. NetFrastructure is a product I designed, built. It was a great technical success, not necessarily a great business success. Interesting technology, and I'll talk about that in a minute, because that's what we're here to talk about. The basic database engine has been in mission-critical applications for about 4 years. It's been very heavily modified for the MySQL environment for a variety of reasons. And it's being extended and integrated into the MySQL environment. So basic architecture has been in place for some time. Making it culturally compatible with MySQL is somewhat of an effort, which has certainly been keeping me busy for a couple months. Okay, what Falcon is not is, first, it's not an InnoDB clone. It's completely different technology from InnoDB. It's not intended to be a plug-for-plug replacement. In many cases, it will be in the same ecological niche as InnoDB, as a transactional, high-volume, high-performance database engine. But it is not InnoDB, and it will have many functional differences. Its concurrency control is radically different. Secondly, it's not Firebird. Firebird is the open source version of the Interbase database. I started Interbase in 1984. There was a lot of nonsense in the trade press around the time that MySQL acquired NetFrastructure that they were getting a rewrite of Firebird. Nope, completely different technology. And if anybody knows anything about Firebird and cares to ask, go ahead and ask. We have more expertise on Firebird here than probably any other room on Earth. It's not a Firebird clone either. Like I say, different technology, and I'll talk about that in a few minutes and why it's different technology. It's not a standalone database management system. In fact, it could be run that way, except that the API isn't exposed. But it is, unlike most storage engines in MySQL, it's a full-fledged database system in itself, which means it's got its own SQL parser, compiler, and interpreter, and does all sorts of good things. But mostly through MySQL, it uses its internal engine for managing system tables transparently, but the interface that you see is the standard MySQL interface that you've been using for quite some time. Yes?
If you submit a query to MySQL, does it pass that SQL through, or does it still do its own, or does MySQL do its parts and call it again?
Could you ask that again?
The SQL query,
yes.
Is that handled by MySQL?
That's handled strictly by MySQL.
Okay.
MySQL parses it, compiles it, optimizes it, and then calls the storage engine on a record-by-record basis. So it's a record-level interface rather than a query-level interface.
So add that into MySQL, simply leave out the code, or is it still saving it?
No, actually, it just goes. It goes in as a. As
Chip,
a
the question is, do you leave out the SQL parser so that make the engine smaller?
no.
So it's still there.
Okay. No. And it's necessary because the Falcon engine uses SQL internally heavily, so to manage its own system tables and so it can wake up and know who it is, it needs a SQL interpreter. The entire engine, the infrastructure engine, is on the neighborhood of a megabyte, so it's not a big thing, and we leave a lot of it out. And of course, it's not infrastructure. Infrastructure, in addition to a database engine, has a tightly integrated Java virtual machine. It has an integrated search engine, and has an integrated page generation engine, and is very oriented towards pure web applications. Okay, I have been wandering around the database world, I guess, technically, since about 1969. I mean, my very, very first job was over in Tech Square for Computer Corporation of America, 1969. What?
I worked there 16 years.
Oh, really? Well, I was employee number 5 or 6, and this is when we did everything on punch cards. You remember? How many people here know what an 029 key punch is? Wow. Okay. Amazing.
People here have used one.
How many have used one? Fine. That's everybody who's right. Terrible. Why were computers funded? I don't know why. Put out a couple databases when I was working for DAC. Was there for about 10 years, including RDB Elan, which was the first of the RDB products, and then it became Interbase. So if I compare, if I want to compare the world in 1984 when I started Interbase and it shipped RDB Elan to the world now, is a huge difference. Back then we only had unit processors. SMP really hadn't penetrated past below the mainframe level, and even there was exotic technology. Now, I think the cheapest I've seen Best Buy is about $6.99 for a dual core SMP machine. CPU performance from 1984 has gone for about 1.7 MIPS, which I think is what a 780 was generally rated at, to about 4,200 MIPS, which is a conservative rating of a unit processor Opteron. Just a huge, huge jump in CPU performance. Address space has gone from 32 bits to 64 bits. To the uninitiated, that's only doubling it, but we all know it's a great deal more than that. Memory speed has gone from a basic 1 microsecond, which was the memory access time on a 780, to 7 or 8 nanoseconds for a cache hit. I mean, everything is just blindingly fast. Medium-sized system memory. When we started Interbase, it was mostly on workstations, Sun and Palos primarily, occasionally backstations. On those machines, an entry-level machine was a meg, a big machine was 2 megs, a maxed-out machine was 3 or maybe 4. Now, when you buy your 695 dual processor SMP box from Best Buy, it's likely to come with a gigabyte. Actually, I noticed last week's flyer, most machines that are above $700 now have 2 gigabytes on them, and if you want to go up to $1,000 for a computer, we're now looking at 4 gigabytes. So that's a huge difference. Large systems, 16 megs was about as big as you would run into a 780. I don't think I ever ran into one much bigger than that. Now memory's maxed out, and if you're going to 64-bit, who knows? I don't even know what people are running. In contrast, typical disk access time has gone from about 20 milliseconds to 7 milliseconds, and not quite a factor of 3. So we've got a huge difference in CPU performance, a huge difference in memory speed, a huge difference in memory size, and really not much difference in disk space. And this has a lot to do with how you design a database system and where the problems are. And last, in the bad old days, 100 users was considered a really big system, and now, for a web application, 10,000 users is considered, it's kind of a so-so web system. The applications that have also changed. 1984, Oracle was pushing decision support. I mean, decision support was a euphemism for slow and unreliable. And Sybase pushed OLTP, and then we had data mining. And you know, where I think the future of the world is, at least the foreseeable future, is the web. That's the only platform that I care about strategically. And the web has different characteristics, substantially different characteristics for a database system than the other applications. So there have been some significant changes in skill levels of people who use database systems. DBAs have gotten a whole lot smarter than they used to be. It's a survival adaptation. The ones that weren't real smart, you know, are now pumping gas or practicing law or something like that. And a great deal harder to find. My goal when I started Interbase was to eliminate DBAs as unnecessary, and it succeeded in many areas, but it didn't go there. So I'm going to have to throw in the towel and say that DBAs are going to, their jobs will be secure even after Falcon ships. Another, I dare say, is that the skill level of application programmers is down. In fact, it's way down from what it used to be. When you had to cram functionality into what now, in a computer now, that wouldn't be considered suitable to drive a decent parking meter, there was a natural winnowing. People learned to cope with environments. They learned to hand optimize. They learned to understand the environments. They learned to understand trade-offs. And with machines as fast as they are now, and with memory as big as it is, it's a very forgiving environment, and the emphasis on getting something out soon rather than get something done well. So where in the past you could had a reasonable expectation that the people who are going to be writing the applications had a pretty good idea of what they're doing, that's now a very unwarranted assumption. And that there are assumptions we could make safely in the past about the people who are building the applications, so we can't anymore. So I think that also has to be a significant consideration in the design of a database system. And finally, expert design has just taken a whole different meaning. Now expert design means that it's pretty, that the colors match, that there's an aesthetic balance to the sides of the page, that the fonts are well chosen, rather than it's a well-architected product. And probably that's correct, because the human interface is more important than the invisible stuff behind it. And probably the better we swallow that lesson, the better off we'll all be. But it's a different world. Change in applications. Databases are much, much larger. Delete, really, you could leave it out of SQL and probably nobody would notice. People do like to keep stuff around for archival purposes. I mean, this space, for all practical purposes, is free, completely free. And so databases get much larger, and we have to cope with that. Second, there are many more queries per human interaction. When you're running a dynamic web application, for anything but a non-trivial application, you're probably looking at in excess of 24 queries per page, generating the boilerplate, generating the content, generating what happens to be going on this side, generating whatever your site navigation is on the left. If all of, yes?
Is that because people are not using the joins well, or just because they're not appropriate for the situation?
It's because people have learned to develop applications where the choices are all visible. And that there are many ways to run an application. There's not a single way of drill down, and making those all visible means that people don't have to hunt and look under buttons and under menus. So there's a good reason for it. I mean, the people on the web have really figured out how to compromise computer applications the way people either like to work or can learn to work. And I think that makes for very good applications, much better applications than we had in the past. If you compare, a modern web page to a client-server application where you have, file, edit, blah, 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 help, you've got a dozen options, and you go to a dialogue, and another dialogue, and another dialogue. Those are very hard to use applications, but they're also computationally very cheap because you're basically putting together a static set of GUI objects and really only one page of content. So in addition to everything else, modern database systems or database systems that are oriented toward the web really have to be able to grind a great deal more queries. And it's not just how many records per second you can find, it's how many queries per second. There are many few rows per result set. Gone with the beloved key punch is the line printer, and the idea that you're going to produce a 1 foot high listing that somebody's going to look at. Now that may be the logical equivalent of a SQL query, but in fact, presenting a screen full of information is what people want and generally want to do, so you go in with some specificity. So you do more queries, you get fewer results per result set. Latency is a great deal more critical. It's a great deal. We had somebody from Google coming out and talking at the last engineering meeting, and something that Google is intensely sensitive about is that people have about, I think it was 700 milliseconds of attention span. That if they don't see what they want within a very, very short period of time, and it's measured in like seconds or fractions of seconds, they'll go someplace else and do something else, and you've lost them. So when you have a situation where you need to do a dozen or 2 dozen queries, and you have a requirement to get something up really fast before the person goes to your competitor, you have got a different world than decision support or OLTP. Blobs are also much larger and much more important than they were in the past. Blobs are kind of an interesting case, and one that's kind of near to home. When I was working for DEC, I had a boss who went around and said, blobs, blobs, we've got to have blobs. And of course, he didn't know what a blob was. Of course, nobody did, but he really liked the term. I don't know, he'd seen a movie preview or something. And I don't even know whether it was Cleveland that got eaten or Cincinnati or something. But one day I found myself in Colorado Springs, where my group was located, and Boston was snowed in, so I sat down with a pen and paper and a pencil and decided to invent the blob. And said, yes, that's how it's supposed to work. And I had an enormous amount of trouble selling it inside a deck. I said, well, this is the way you put documents or pictures or images inside of a database system. And they said, well, why do we want to do that? I mean, database systems are for numbers and strings. I said, well, because you might want to put a picture in there. I said, well, that's completely crazy. Or you can put that in the file system, put the file name in the database. And we had this long war over it. And it kind of boiled down to, on one hand, DEC had never lost a sale because they didn't have blobs. No customer had ever asked for blobs. None of the competitors had blobs. But I managed to just cram it down their throats anyway. So there we had blobs in the first version of the RDB architecture. Interestingly enough, however, the RDB VMS guys decided that the term blob was unprofessional, and that it was just a little bit too whimsical, and they were worried about their image, so they called them segmented strings. The idea that you could transfer them in pieces. And kind of even more interesting, a year later, after when Interbase had blobs, and we called them blobs, the world immediately fell in love with them. It took about 18 months for every database system to have them. But when people went back to DEC and said, well, what are you going to have blobs? Their marketing guys would say, well, that's a good question. We'll try and get back to you in the next release and tell you when we'll have them. So storing big stuff, PDFs, documents, Word documents, image is critically important to any web application, to basically any application. And it's now critically important that those things perform very, very well. It's just a fact of life, they're here. And last, and this is one where I'm having kind of the same experience inside of MySQL that I had selling blobs inside of DEC, is free context search. How many people here have ever been to Google? How many people here have not been to Google in the last 4 hours? Okay. Now, that suggests something about the way people use the web. Database guys have never mastered the idea of free context search, where I want to ask about something, and I don't know whether it's in this table or this table or that table or that table. And I say, well, you just go find it. You know, and look for Ann Harrison. And I don't care whether maybe she's an employee, maybe she's a developer, maybe she's a support person, maybe she writes 50 comments. It could be a dozen different places. Well, you tell me where she shows up, and I'll find out which one I want. I mean, it's a natural way to do it. This is the way. Without that, the web would not exist. Database guys haven't mastered the idea of search. They have the SQL model. Search doesn't fit in SQL, can't be made to work in SQL, because you don't want to say, well, if you have a municipal site, you want to say, find content from departments where responsibility contains, no, it's like dog tags. No, that doesn't work. You want to say dog tags, and you want to find out how you get one. So this is someplace that we aren't yet, and we've got to go. It's inside of the Falcon engine, but being able to get that exposed in a reasonable sort of way is going to take a little bit more work. And most of it's cultural work and not technical work, which I think is interesting. Okay, what have I learned in between 1969 and late this afternoon? Actually, to be fair, what did I learn between 1969 and the end of April when I put the slides together for the talk? So maybe I've learned things more. CPUs in memory are vastly faster than they used to be. Secondly, disks relative to CPU and memory, relative to CPU and memory, are vastly slower than they used to be, and getting slower by the day. Multi-generational concurrency control. MVCC is the MySQL term for multi-generational concurrency control. I'll talk about that in a few minutes. And I use in print MVCC so they can understand it. But I invented the term, so I'm going to call it multi-generational. So that's the way it is. So when I say multi-generational, you can think MVCC if you'd like. You have my permission to think that. Multi-generational concurrency works. It's an alternative to record locking and has a lot of advantages. Next, for multi-generational systems, having multiple generations of records on disk is a real pain in the butt. And that's the technology that I used in RDV-Align and what I used in Eaterbase and it's inside of Firebird. If you have multiple versions of a record on disk, sooner or later you've got to do garbage collection. And as soon as you start doing garbage collection, you introduce both a little performance surprise here and there and almost endless arguments. And the performance issue is bad enough, but I got really tired of the arguments. So I said, okay, I'm not going to do it that way. I'm going to do multi-generational memory and let the disk be single generation. Yes?
Did that have any effect on the frequency bugs in the code as you were doing this?
Oh, it has a huge effect on everything.
Did it help or hurt?
It's designed around that, and from that decision, basically all other design decisions flow. Is once you decide that you're going to have transaction state in memory, and I'm getting a little bit ahead of myself, but once you decide you have transaction state in memory, now you have a total different way you conceptualize a database system. Okay, going back to what I've learned. Web applications are intrinsically better than client-server applications, and happily through the future. So I don't think anybody here is going to argue. I know the old guys here aren't going to argue. Maybe the young guys will, but there you go. And they're better because they're easier to use, and it's a universal platform, and you don't have to install anything on your computer. And I hate installing stuff on computer. I consider any time spent administrating a computer comes off my lifespan. I don't like it. And finally, and I think this is absolutely important, is that people have a whole lot better to do with their lives than tune databases. I can't think of anything more boring than tuning a database. Okay, so when I sat down, even before I invented the god-awful term netfrastructure, for which I've got nothing but grief from MySQL people. In fact, I think the very, very best thing about the acquisition is renaming the engine Falcon, which is so much easier to say than netfrastructure. And if you ever have to spell it over the phone, oh boy. Okay, here, first goal. We've got these marvelous new computers that have completely different performance characteristics from the old ones. Let's use them. Let's exploit large memory for something more than just a bigger page cache. Database guys historically have considered that, okay, we have a page cache and the computer gets bigger, we'll make a bigger page cache. There's better things to do with that memory. Second, we have enormously fast processors, and now we're getting processors coming out of our ears. When your $700 computer's got 2 cores this year and it'll have 4 cores next year, and for another $500 you put 2 of those suckers on the same board, we've got processor cycles coming out of the ears. Let's use them for something intelligent. You can start doing data migration, taking advantage of a memory hierarchy, moving stuff between layers, and use some of the processing speed. Don't pretend we've got a uniprocessor and we're going to use it for one thing. We just can do a couple things in parallel. Let's actually put them to use doing something interesting. Another goal, designed to eliminate trade-offs. I hate trade-offs. I really dislike trade-offs. Do you want to be skewered or do you want to be shot? I mean, wow, what a great decision. Looking for algorithms and techniques that don't require the human tuning. And let me give you an example, one that I've been using for quite some time. And that is the choice between a clustered index and a non-clustered index. For those of you who are blissfully ignorant of this silliness, clustered index is where the record is stored on a page in index order. So if you're reading by primary key, you get the records in the same order. And there's a big trade-off on whether you're going to do a clustered index or a non-clustered storage scheme, and how it's going to act with foreign keys and all sorts of stuff. Well, I hate that stuff. The problem with clustered indexes is that you've got to get the balance right, or instead of being optimal, it becomes passable. So what I did one of the ideas I had when I was doing RDB-Elan was, well, why don't we do things differently? We'll use a traditional B tree, but we'll use record numbers that are assigned in a reasonably dense sort of way. When we're going to do an index retrieval, we'll scan the index first, rather than going index record, index record. We'll scan the index first, we'll use the record numbers to set bits in a sparse bit vector, and then we'll go back and process them in bit order, which happens to be physical order on disk, so all indexes have the same performance, and at most you're making one pass over the data. And that eliminates the choice. Well, it turns out it gets better than that, because if you have an AND of 2 things that are indexed, you can just take these 2 bitmaps, and before you do any retrieval or look at any records, you AND them bitwise, and lo and behold, you cut down the number of records you have to look at by a very substantial portion. You can also do ORs that way, and it's all kind of neat things. So, this is just an example of some place where you can take a nasty trade-off where somebody has to make a decision on how to structure a database and eliminate it just by making the system smarter, and then therefore the people can be less smart. I have to say, I was at DEC when VMS was born, and I really hate VMS. I did put out the first layered product on VMS, so I think I'm entitled to criticize it. The thing that I hated most about VMS is tuning. It had 257 tuning parameters, and if your system ran like a dog, which 780s usually did because they were dogs, and you complained to the VMS group, they would say, well, you don't have it tuned right. You say, well, how do we tune it right? So, well, that's for you to figure out. Yeah. The hell with that. Okay. Architectural overview. The basic idea, from a conceptual point of view, is that Falcon is an incomplete in-memory database with backfill from the disk. So the basic idea is that the database is in memory. It's not all in memory, but when you try and access something that isn't in memory, it goes out, brings it in. So the records, when it's running, live primarily in memory, and if they aren't there, we'll go get them, bring them in, and any subsequent references, they will be in memory. It has two quite independent caches. It has a traditional LRU, and for those of you who aren't database diehards, that's least recently used. It has an LRU cache for disk, like all database systems. But it also have a much larger row cache for recently referenced records. And this is typically set for between maybe 500 megs and a couple gigs. So that's where your primary use of your memory on the system. And the reason that you have a row cache, actually two perfectly good reasons. One is that it's a much more efficient way of using memory for a cache. Because if you have one very popular record, so they say that's 20 bytes long on a 4K page, if you want to have a page cache, you're using 20 bytes of 4K of memory. Where if you're putting that in a row cache, you've got 20 bytes, plus probably another 16 or 20 bytes to keep track of it sitting in memory, in main memory. So in terms of efficiency, it's on a per record basis rather than a per page basis. It's a great deal more efficient. What you really want for anything, any high volume database, or for any web app, is you never want to hit the disk. I mean, disks are where you flush updates to. They're not for reading, and almost all data almost all applications are heavy, non-uniform data access. There's always the popular records that people are looking at. The stuff that happened 15 years ago is really of very little interest. You can go read it if you need it, but there's no reason to waste memory for it. And finally, it has a single serial log for group write commits. The way, and I'll wait a minute and explain that on the next slide, I hope. Okay, as I said, it's multi-version in memory and single version on disk. And what I mean by this is, if you reference a record in Falcon, pull it off of disk, stick it in memory. When you update that record, it'll create a new version in memory, pointing to the old version in memory, and each one, the new one will be tagged with the transaction that created it, and within the engine, it has enough smarts to know what records it should look at and when it should follow the old pointer. So the model in multi-generational concurrency control is that every transaction sees a stable view of the database that is consistent with the picosecond that it started. It sees an absolutely consistent view of the database. It does not see concurrent updates. Old versions are kept around as long as a transaction can see them. So it sees a consistent view of the database. And there's a couple things that are very nice about this. The most important one is that readers never block writers. Since it keeps old versions, if you're reading, you can produce a very long report if you really need to, and you're not going to stop any updates at all. And that's very nice. Another is that it gives you the basic ACID properties. And I'm not going to embarrass myself by trying to remember. And quick, ACID.
Atomic.
Atomic, yes, we want And
Consistent.
consistent, which means if you add up a column of numbers 10 times, you get the same number every time.
Independent.
Independent, what's the difference between that and consistent?
What's the difference between that and and atomic?
Okay.
Two transactions do not interact.
That's right.
Atomic means that the whole thing happens at once, or it doesn't, or the whole thing happens or doesn't happen.
Explain it to these people. I'm never going to learn it.
And
And last one is durable. It says when you commit, that record is going to be someplace where you can get back to it. And I define durable by meaning that record is sitting in an oxide someplace, plus or minus the operating system. Back in the olden days, when you told it to write something, it used to write it. Now, almost all operating say, okay, I'll make a good faith effort to write that sometime.
the operating system is bad, but the disk cache itself, where the operating says, oh yeah, I wrote that, no question, and the disk cache has it instead.
Yeah, right. So there are issues there. We know how to deal with those too. Okay. Okay, multi-generational in memory. Updates aren't flushed to the disk until commit time. Yes?
To do this kind of thing, you have to turn off virtual memory, right?
No. We'll get to how it works. And you don't have to turn off anything.
When
There's
you have the
there's
risk
big-
of stuff being swapped out into virtual, on disk from virtual memory reasoning.
I don't want to get too far ahead of myself, but all of the civilized operating systems, and most of the uncivilized ones as well, have a mode where you can do a direct write, a serial write to the disk. And it's atomic.
The question is, you overflow memory and you start swapping.
Oh, wrong question. Yes. Actually, what you want to do, there's two things. One is that there is control over the maximum record cache memory you're going to use. And when you exceed that, it will kick off a scavenge process to kick the older stuff out of memory. And there's also a lower bound, which is its target. So you set kind of a high-low, and when you hit the high, it whacks it down to the low level, then gradually builds up again. There is a mechanism which isn't quite implemented. No, it's not quite implemented. It's not implemented. It will be before GA, where if it notices that you're doing a very large update, like a mass load, rather than keeping the new record versions in memory, it'll write them out to a scratch file. But the model is still the same. The transaction state still lives in memory. The records may reside temporarily in a scratch file, and that fact doesn't have any significant effect on performance for a variety of reasons. But you do want to set your maximum record size substantially below the amount of physical memory you have, because swapping's bad. Paging is worse. Okay, transaction status in memory. The entire database, with the exception of the serial log, is in general a single file. And this is quite a bit different from all of the other MySQL storage engines, which tend to have a separate table for every file. So it's just a different approach of doing it. There's a single page space and table space, table segment, data segments, and indexes are all taken out of the same data space. Yes?
Does that make it hard to recover from disasters?
No. It doesn't make it harder to recover from disasters, but it's still hard to recover from disaster. No, excuse me. Let me say. It's hard for me to recover from disasters, but once I've got all of that working, it's easy for you.
Okay.
All of the hard stuff is my job. The easy stuff is yours. That actually doesn't make any difference whether that's a single file or multiple files for that. Yes?
Sometimes depending on the usage of different tables, you may put aside that certain tables should have their own disk or whatnot. Is there any way to accomplish the same thing with some type of higher level thought of, let's tables are used and to spread your disk usage across your tables, and that, like, some things are serial usage, some things are.
No, there isn't, and no, that doesn't make any sense. Because once the system has been running for any period of time, you've got the popular record sitting in memory and you're not going at the disk anyway. So the idea is to avoid going to the disk, not make going to the disk faster. And
Explain about the log files, let's just get into that later.
the log,
The log files.
yeah.
We'll get to that later, or do you want?
We'll have a better time to come back to it.
Okay.
Because I want to talk about the data migration before I get there.
Jim, a couple more questions?
Yes, oh, I'm sorry.
Your single database, you ever run that in a raw partition like that file system completely?
We haven't done that with Falcon. We have done it with Firebird, with no significant performance difference, less than 10%.
With modern machines, there's so much processing that you can avoid.
Yeah, what you pay in terms of having to worry about your partition is not worth the performance difference that you see.
But if I understand with read, your popular records are in memory, but if you're writing, if you have something that's doing lots in the database, and you have serial writes, it would make sense, I would think, to have a single head that's just kind of writing sequentially.
Hold the question. Hold the question.
Jim, can you repeat the questions when you have them studied?
What?
When you get a question and you're answering, can you just repeat it so that
Okay.
everyone can hear it?
Okay. The question was, what about rights? And I said, hold the question, come back later. Those of you listening on tape can see me waving my hands right now. Okay. Blob repositories, it's actually something that Netfrastructure has, which is really nice. That is large blob data like PDFs and JPEGs really can benefit being managed differently. And something that we have in Netfrastructure, the concept of blob repository, it's a series of files that you have an upper limit, or every month they'll kick over to a new one. And they're designed to go well with replication. So if you have various replicants of the database, they'll have equivalent blob repositories. So when you recover a database, it's not necessary to recover the blobs as well. As in a modern database, the blob storage totally dwarfs the active data storage, the table space. And getting that out of the table space is really good. But that's the future. And again, future is multiple page spaces. In the drop it, it's not. Okay, the implementation. I'll go through this quickly. The basic implementation model is multi-generational concurrency control, MVCC. This is a nice acronym that doesn't match the words that go with it. Blobs do not stand for anything, incidentally. They're not basic large objects. They're not binary large objects. They're the thing that ate whatever city it was in Ohio. A marketing person at Apollo Computer named Harry McKeever decided that blobs had to stand for something and made it I want to say a retronym, but it's a retro acronym. Somebody invent a good term for that one of these.
The
Yes.
term for it is backronym.
Backronym?
Yes.
Very good. Is that spontaneous or is that well known?
No, that's a commonly used term for that sort of acronym.
How many people have not heard that? Okay, common.
Well, now it is. I heard retronym, which I think is the same thing.
Among common people.
Among common people.
As well.
Anne, could you write down acronym?
Yeah.
Yeah, cool. Okay. Multi-generational concurrency control. We probably, yes, we have put in relaxed consistency controls for read committed and dirty.
You put in dirty read?
I don't know what I put in. I forgot. I don't pay any attention. this is something that really irks me, and that is the whole idea of multi-generational concurrency control, is that you get real concurrency control, near serializable, but you see an absolutely consistent view of the database. It's something that you can just build into an application, and it's dirt cheap to implement. And the alternative is record locking, which you can build a serializable system with, but requires great skill in terms of programmers, and you have to keep hiring good programmers to keep it from deadlocking and having the performance go south. And now that we've got a technology to do currency control that's consistent with very high performance and high transaction throughput, the miserable SQL committee standardizes non-consistent transaction modes. Drives me berserk. End of rant. Okay. And we will probably at some point, and I haven't done it yet, put in a strictly serializable mode. I'm going to leave it as an exercise for the audience to come up with the reason why multi-generational concurrency control is not serializable. And I'll give you a hint. If you read Bob Gray's, or not Bob Gray, Jim Gray. Bob Gray was a roommate in college. Jim Gray's early work, you'll never figure it out. Okay, indexes. Falcon indexes are traditional B-tree indexes with prefix compression, so they're variable length. Unlike some of the other storage engines, there's no data in the index except the key itself. Yes?
On the, not on the leaves, but on the higher indexes, do you do any chopping of the
Suffix,
the
no.
No suffix compression, so just prefix.
Suffix compression eliminates trailing blanks and spaces. Yeah, trailing blanks and zeros, depending on data type.
And,
What we do is, when we generate a key, it takes the elements that go in, the segments that go into the key, and it turns it into a byte sequence that can be compared as unsigned bytes. So the index code is not sensitive to data type at all. And what we do to numbers, you don't want to know. They're really battered.
what's the maximum length of the index key?
That was one of the major changes that we had to do in turning infrastructure into Falcon. And the answer is, the hard answer is 32K, but we don't support that big. It's, I believe, who said 2K, 4K, something like that. It's just it's a built-in constant, and has only to do with the size of a static structure. So we can change that at almost any time. Oh yes, it's an open source project, so you can change it yourself. Yes?
Does any of this mean that it no longer matters what order you put your keys in for a multi-key index?
It certainly has a huge effect on performance.
Okay, so this does not wipe out the need to pay attention to that.
No, not at all. No, it doesn't. I mean, if you have a... Anne, would you like to say something?
Assuming that we get some push-down conditions on indexes,
Yes.
you don't have the same need for a multi-key index as you do in a database that can use only one index per retrieval. If you have two indexable fields in your selection, Falcon can use the two indexes, combine them,
Well, so basically, I should never need to create multi-key indexes in the first place.
unless you need them for uniqueness.
Okay.
If you're always going to do a retrieval based on two fields, by all means use a multi-segment index.
But otherwise, if I'm going to have an index A and an index B, I don't necessarily also need an index A comma B or an index B comma A.
Right,
Okay.
right. I'm not doing very good at repeating questions, I'm sorry.
That's right.
I'm very sorry to those listening at home. As I said, index retrievals are two-stage. First we scream through the index, setting bits, then we go back in bit order and pick up the records. Our indexes are noisy. They have to be noisy because it's multi-generational. If there are two versions of the record, both will be represented in the index, so you have to read the record to see whether it's what you want or not. not just the cost of doing business, but it also means that records are always fetched in what would be physical order. So if you've got 3 or 4 records on the same page, they'll all be referenced back to back, which is a nice performance feature. Of course, after they've been referenced once, they sit in memory and it doesn't buy you anything. But old habits die slowly. There are no performance differences between primary and secondary keys. Just none at all. And this is kind of radically different from DB, where I believe you go through a secondary index, you have to go through that index, get a primary key, and then go through the primary index. And finally, the scanned bitmaps can be combined into a single one. To get this fully exposed in the MySQL environment, it's going to involve a little bit more work, but we'll get there. Okay, now here's the guts, and this will get to all the questions about serial log and how the thing really works. Uncommitted row data is always staged in memory. So if you modify a record, the new version, the old version will exist in memory. If you delete a record, there will be a stub saying, I'm gone, pointing to the version that you had deleted. Each transaction has a list of the records that it modified, so it knows what it's done. On the commit operation, row data belonging to a transaction is first squirted into the serial log. And what I mean by serial log is logically you write in a serial order, and then it does whatever the operating system requires you to do, so it's written sequentially. And most operating systems have such a mechanism, and without being queued or cached by the operating system. So when you say write, it's going to write them in order, and it's going to, when the write is done, you know that it's been transferred to the outside. So in terms of write operations, this always seems a great deal slower because it's not cached by Unix or NT, but on the other hand, it gets onto the outside and it's where you want. So the model is we do the uncommitted data in memory. At commit time, we write it to the serial log. Then we write a commit message at the end of the log, and we flush the log to disk. And at the time that the log is flushed to disk, the transaction is committed. And since the commit record is at the end, the last thing to be written is the commit record, and no matter what happens, we'll be able to reconstruct that transaction. So it is a single write commit. We also do a very simple trick, and that is if there's a serial write ongoing, if somebody else does a commit, they'll just write their commit record into the log and join a list of people waiting for the next write. So as soon as one serial write finishes, the next write will start immediately, and everybody who's queued themselves will be committed at once. So you can do many transaction commits on a single write. So you can have, no problem getting up to, a couple thousand transactions per second, legitimate update transactions per second on this piece. Okay. So on commit, row data is copied from the transaction in memory to the serial log. Post commit, after the write is done, there's a Gopher thread that's going to wake up and find all of the record updates in the serial log, which is still sitting in memory, so it's not going to read it unless it's gotten really big. It's going to then find them, and then it's going to migrate those updates back to disk. So the actual data doesn't make it to disk until way after you've done your commit. It could be 30 seconds, could be 10 seconds, doesn't make any difference because it'll eventually find its way back. And if it doesn't find its way back before the system crashes, the recovery process will take off where the other one left off. And then periodically, the page cache itself is flushed to disk, and that's done by an internal scheduler, and then by default that happens about every 30 seconds. And there's some interesting logic about what happens when the serial log gets flushed before the pages, or the pages get flushed before the serial log. And I'll bore you to death on that in great detail if you want to know more about that. But the basic idea is, first, records are written to memories on committed records, then they're flushed to the log. At commit time, post-commit time, they're copied from the log into disk images in the page cache, and then periodically the page cache is flushed back to disk. And when all of that is done, the database is stable again. The one exception to this is blob data. Blob data is handled differently since there's no, you don't never update blobs. As soon as a blob has been, when a blob is being written, it's written directly to page images in the page cache. As soon as the write of the blob is complete, it's turned over to another thread, a page writer thread, who starts writing blob pages out. And before a transaction commits that has outstanding writes, it'll just wait for its blobs to be written out to disk. The idea is that we don't want to waste time putting things like PDFs or JPEGs in the serial log. That's just a big waste of space, time, and effort. So blobs are handled differently. Now, yes?
What happens on a rollback?
On a rollback?
Yeah.
The fact that we have done that is in the log. If the blobs are, for some reason, get flushed before the other one, you may end up with some lost pages. That's no big deal. It won't affect performance, but you may have some lost. The worst case is you may have some lost pages in that case.
I'm not really the lost pages. I mean, if you do rollback, does the blob get rolled?
Oh, if you do rollback, it'll go. It knows what blobs it's created. It'll just find them and delete them.
But if you're modifying an existing, it's not doing an update on a blob.
You don't. Okay. In Falcon, you do not update blobs. You create new blobs. You can replace a blob in a record, but you do not update blobs ever, and that's very important. The way Falcon handles blobs is radically different from the way MySQL, other parts of MySQL handle blobs, and that is they're not stored as part of the record. They're stored as independent objects in a different table, in different data space, and all you have in the record is the blob number.
But you're not providing the model where I can basically treat it like a file open and change, 2,000 bytes in the middle.
Absolutely not. There's no update in place. There really can't be in a multi-generational system, because you may have somebody else reading it. But nor does it make sense to try and replace the... I'm just thinking of Forrest Gump, where you're replacing a character in a photograph with another character. And that's what I think of when you do a blob and update in place of the blob.
But there are other things that can be stored in there.
Yes. No. In Falcon, blobs are not updatable. If you want to store a different blob, it's a different blob, and there's a garbage collect mechanism that will cause the old one to go away when no one cares about it anymore. Let me just say in passing, tiny blobs are automatically mutated into strings. I just find the idea of tiny blob so infinitely bizarre. Yes?
The thing you say is no longer not available. Was that available in any of the other storage engines? Updating a blob in place?
Why do you care? If you can change the value of the blob field at the SQL level, why do you care if he's munging it in place or sticking a different place and changing the pointer?
I can answer that question.
You can care. Well, why should he care?
Something I have learned is that any rational prediction about what other storage engines do is unwarranted. There is...
Your rule one you said was tuning is a waste of time. The system should just do it right. So if he says he's taking away a tuning choice from you so that the system always does it the fast way, be happy.
I was just asking whether there's some piece of SQL that would no longer work that somebody might be used to from an NRDB because you did this.
Well,
This should be so far below the SQL level.
Okay.
That unless you're coming in on a really dirty API that was
The actual-
engine specific, you won't see it.
Okay.
excellent point. You can't do that in SQL.
That's why I was asking, is there, okay. You can't do this in MongoDB, then I don't care, you can't do it here either. That's all I was asking.
Okay, all right. Okay, data reliability. This is the really hard part, which is to say this is the stuff I'm doing right now, and it's hard. The physical structures, the on-disk structures, the pages are protected by what's called careful write. And careful write is a technique where the pages are written to disk in such a way that the database is always valid and always consistent on disk. It's tricky. Firebird/Interbase and RDBLon run without any sort of journaling, any sort of log at all. It's just based on careful write, so it's doable. Falcon, because the way we do commits, to avoid a bottleneck, we don't depend on careful write because we don't want to flush the cache on commit time for performance reasons. So the pages on disk are always valid and always consistent, and it's really a very simple thing, and that is that if you're going to write a pointer to another page, you write the page that's pointed to before you write the pointer. That's not so tough. And the second half of it is the serial log, where we log all sorts of logical stuff, like what records we're updating and what's the state of transactions. But we are also using that, we're logging physical information to reconstruct some things that have happened that are important if they don't get written from the main database pages if the system crashes. If the system doesn't crash, none of this makes any sense at all. Okay, the serial log is quite a bit different from most of the database systems you probably run into or other storage engines. It's a combined single log. It's a do log for post-commit data migration, where it's going to migrate data from the log onto disk pages and disk images in the cache, and then to disk pages on the disk. It's a redo log for post-crash recovery of data. So if you have a crash, if the server crashes, and this is not the rollback path. This is a hard server crash, like you tripped over the power cord, or you killed the server without shutting it down. Or there was a bug there, or it happens. If the server stops abruptly, it's a redo log for reconstructing what had happened. And it's also an undo log for post-crash recovery for transactions that were rolled back before the system crashed. Okay, last. This is my secret agenda for the database industry. First, I want to get rid of varchar. I hate varchar. It occurred to me about 6 months ago, a little bit more, that why do database systems have an upper limit on strings? Punched cards. That's the only reason. Punch cards had fixed fields, and that got mapped onto tapes, and IBM's idea of disk was kind of a tape that run around in a circle, and it all is based on fixed length records. And once you get rid of the idea of fixed length records, there's no reason to have fixed length character strings.
But punch cards was 80, and the usual limit is 255.
Yes, but this is progress.
Figured out that the byte went up to 255.
Think of a punch in column 73, which is a continuation, or Fortran. No, Fortran is column 6. Think of that, and you can count. Okay. In fact, what Falcon does, and I thought I'd put it in the talk. I hadn't done it when I gave the talk at the user conference, and I have since, is that the record, call it semantic data encoding, it's based only on the actual data rather than on the declarations. The declarations have absolutely nothing to do with the way the data is stored. You can declare a string to be a varchar2 of 20,000 characters. You can declare it as a tiny blob. You can declare it as a single byte fixed length character string, and if it contains the letter A, it's going to be 2 bytes. Likewise with numbers. You just store numbers. Little numbers are smaller than big numbers are bigger than smaller numbers. But it doesn't make any bloody difference how big it is.
Just the
That
integers, not the
a 7 is going to take up a single byte. We've got the format is very, very simple. It's a type code followed maybe by some significant characters, but there are specific byte codes for numbers from -10 to about 60, and those are stored as a single byte. There are other byte codes for strings from 0 to about 40 characters. There are other byte codes for strings that have a 1 byte count, a 2 byte count, a 3 byte count, and this is purely based on the actual data and not the declaration.
What about sign versus unsigned?
Excuse me? Yes?
Sign versus unsigned, same thing, byte code for sign versus unsigned?
You don't see them.
Does that mean that your database is completely, the actual byte structure of the database is completely independent of the machine architecture? You just take it from one to another without having to do any conversion at all?
No. The question is the file format such that you can take it from one machine architecture to another machine architecture? And the answer is no. Someday, maybe, we'll relax that. Something that Dan has done recently for Firebird, which has very similar on-disk structure, is to put in the code to when a page is written, to flip the bytes and flip them back when it's written. And the cost of it is kind of insignificant. But for reasons of performance efficiency and long-established bad habits, there are binary stuff all over.
Is it only dependent on the endian nature?
It's only endian nature.
Yeah,
Only endian nature.
I assume you still have a distinction between integers versus fixed point versus floating?
Yes. Yes. The way the encoding decoding is done between the MySQL world and the Falcon world is it just asks MySQL, what is this thing? And then it cases on data type. And if it's floating point, it'll squish it and store as few bytes as it can. If it's fixed, it'll maintain that. It has its own format for storing high precision numbers. So it actually has a higher numeric range than MySQL, but happily you can't get at it because MySQL will be a filter on the front end. Oh, yes?
Do you feel that it's not the job of the database to enforce a schema or to enforce limits on the data?
No, I don't think it's anybody's, I don't think people should have to decide how long somebody's last name can legitimately be.
Okay.
I mean, how long is the last name? Any guesses?
Well, when we got married, my wife's was, since she hyphenated, was longer than most databases.
Yeah.
Right.
Yeah, I mean, the joke is what happens if two anthropologists get married and you end up with a fourth?
My wife was trained as an anthropologist.
It's only a problem with cultural anthropologists. Apparently physical anthropologists don't do that. Ms. Harrison.
On the subject of enforcing string lengths declared in the schema.
Yes.
That's handled at the server level, not at the database level.
So you can still force
If-
data
Oh, yeah.
numeric or to be.
These are his secret agenda. He hasn't succeeded in convincing the rest of MySQL that you ought to be able to declare something as a string and not worry about it.
Right.
So far, they're still in the varchar 20 world.
Right. No, and certainly I agree with things like strings, but sometimes you do want to enforce something like an unsigned versus a signed or an upper limit on a integer or something.
I do have a, so if you declare something a string and then you index it, and somebody puts in a string which is too big to fit into your B tree, what happens at that point? You secret agenda.
I mean, if it's bigger than 4K,
Yeah.
then they should fire that person and get somebody with a shorter last name.
Just printing the check is going to be.
I might have to prefix index anyway.
That's the one
Yeah.
The only constraint and it's an index constraint, not a string constraint, is the maximum index key. Let me say something else, and I haven't mentioned in here, and that is, I don't believe in recreating tables. I believe in very fluid metadata, and all of the database systems I have done, when you do the metadata update, it just changes the metadata and starts storing stuff in the new format. In fact, this doesn't even do that because there's no such thing as a format. But anything can be done online. That's not the MySQL philosophy yet. In fact, I don't think any of the storage engines can really handle dynamic metadata except Falcon can and has from the beginning. Falcon was really intended for a web application where it's up, 24/7, 52 point whatever. So it's just up, and you never have to take it down. Every once in a while, you've got to, take the machine down and dust it off. But other than that, no. I should probably add that to my secret agenda. That one's going to take a long time.
Automatic.
Yeah.
You've got several more.
Oh, I do. Adopt a security model. Oh, let's see. Replace tiny, small, medium, and big integers with number. You shouldn't have to be able to tell the database system advanced what the range is. I mean, what happens if there's a brilliant advance in medical science and we have like a year 2K problem with people's ages? This is silly. A number is a number is a number. I mean, 1 digit, 2 digits, 10 digits, 19 digits, 25, who cares? Number. And that's the way Falcon is now handling numbers. Adopt a security model useful for application servers. There are 3 pig-headednesses of database people. Having been one for a long
Count
time.
everything. Before they start.
There are 4. First, they count everything. Something I noticed a long time ago, and this doesn't have to do with anything, is that object people don't understand databases. Database people don't understand objects. And it's been this way from the beginning, and I don't understand it. I, of course, understand both very well indeed, with great depth, and it drives me nuts. The SQL security model is incredibly stupid. How many people have heard of application servers? Anyone? Okay, fine. Right. Well, when you have an application server, you've got the client talking to the application server, and the application server is talking to the database. And gosh, when you go in to Amazon, it doesn't create an account for you in their database system that then logs on to. Database systems just have to learn that there are applications that are acting on behalf of a client, and it's not going to know who the client is until it's done a database access, so it doesn't know in advance, and it has to have a much more flexible model, so you can attach to the database, then find out who you are, and say, okay, now until I tell you otherwise, these are the security rules that I want you to use. So if you have somebody's administrator, he's going to have one set of behavior. If somebody's an employee, he has another. If somebody's part of the great unwashed anonymous web users, he has a third set. And this is the way the world has to work. And sooner or later, database systems have to recognize this and have to adopt to it. So the security model inside of SQL is useless. And that's got to get fixed. What I would like to see, and what I've implemented in infrastructure, and I don't see any way of exposing it in Falcon, is a usable row-level security filter. It's a filter mechanism. It's really nice and really simple. It's called a filter set, and what it consists of is a list of tables and pieces of Boolean that are applied automatically on any table reference, for any reference for that table. And it's just grafted on during the compilation process, and it's applied recursively. So one table can reference, a filter set can reference another table, and it's really neat, and you just set up you activate, deactivate roles, and records just disappear if you don't have access to them. Solves lots and lots of problems. Yes?
Why is that different than the traditional SQL
It's much more dynamic than SQL views, because you may have 30 or 40 different roles in your worst case, maybe many more roles than that, and you're going to be activating and deactivating them furiously and having the views combinatorially infinitely large.
Filter sets can apply to your views. Your filter sets can apply to his views.
They would be applied automatically to the views.
As opposed to having to explode views, the views you really need by role. Yeah.
One of
And your bitmap intermediate structure makes it affordable.
You bet. Works like a charm. One of the major infrastructure customers is a fairly large law firm in New Jersey. And they have written this wonderful comprehensive application that does absolutely everything that a law firm needs to do, from everything from logging all mail that comes in and generating all mail that goes out, docketing, all client contacts, and case information. They have a single web application that is their internal working application for all aspects of the law firm. This law firm does asbestos litigation, and their clients are insurance companies that have between 5,000 and 8,000 cases each. And this is a way, it's an intranet, so those insurance companies can get in and see what's going on in various cases under careful control of the attorney. And finally, it's their public website. And they put this together with 2 really smart guys and a bunch of summer interns. And the whole idea, of course, the problem with this is that if you expose client data to the public, you're kind of like disbarred, which is kind of a bummer if you're a lawyer. So the idea that the application was written by summer interns meant that they really wanted to have a security model that was enforced by the infrastructure, not the programmer. And oh boy, that is the right way to do things. That is so the right way to do things that it just boggles the mind that it's just not part of. So maybe I'll add that. Yeah, that's on my secret agenda. And finally, last is to teach the database world the merits of context-free search. So if you want to find out about dog tags, you can find out about dog tags without knowing in advance where dog tags are. I think the problem is Unix man pages. And that is, you have to know something about Unix, you have to know about that thing before you want to find out about it, because you need to know what man page it is to find out about it. And this has poisoned Unix programmers from using search?
It's not just Unix. Right? Other vendors, if you look in the hard copy manuals, the index in the back is incompetent. You have to know the concept to find it, either the table of context or the index in the back. And Kurt Vonnegut had great commentary on this as an aside in the opening chapter of Cat's Cradle. An author who indexes his own book as a fool for a patient, I mean.
There was actually a deck manual that had in the index a reference to undocumented features. And the page number was one of those opposite chapter headers, which says this page intentionally left blank. And in Knuth Volume 1, if you read the index, you will find MUG, which is Mixed Users Group, and it references only that page in the index. Okay. So, on that note, questions, as if we hadn't had some questions. Oh, boy, all sorts of new names. Okay.
Is that row filtering by updates, just for read-only operations? Are you filtering on read operations, or are you also doing low-level security?
I mean, filter sets?
Yeah.
Yes, filter sets apply to for read operations, and if you can't read them, you can't write them either. The writing is virtually always under application control. I mean, nobody in their right mind lets somebody over the web do an update, but they often will let somebody just do a query or something that gets turned into a query without a lot of analysis in part of the program, because that's the easy way to do it, and stuff that they shouldn't see just.
That would potentially allow a situation of bugging the application code, let you write data, you use some substance that you can't see.
that,
If there's a bug in, it could be a bug in the application code, so.
that could be,
Yeah.
and it'll, yes, and it'll just
The
disappear.
application line.
In fact, in the net infrastructure world, for example, its internally generated links are, in essence, SQL statements with the keywords squished out. Just that simple, and it's all set up, said fine. This is what it is. You can forge one if you want, but it's not going to get you anything. And that's really the bottom line: is you want to have a system where somebody could, even if he could forge a query, it's not going to do him any good. That I think is really the bottom line on security. Yes.
If everything is, I'm a little fuzzy on this. If everything's variable length, A, how do you determine the length? You just have a count field, and a bit, some kind of barrier? The other is, how do you find things in the middle of the?
Everything is variable length, and to find the fifth field, you actually do have to parse through, but parsing a field is, in almost all cases, a single table lookup on bytecode. The common fields are all fixed length. If it's a large string, then you're going to have to pick up a count and skip over some stuff. And then it keeps track on a per record basis of the offsets to fields as it learns them. So if it's been to that field, it has the offset from the beginning of the record. That's not stored as part of the record. It is stored as something in memory. It costs slightly more to access a field than it does if you had a fixed length field. If you're referencing fields in order, which you do between MySQL and the Falcon world, then it really doesn't cost you anything along, because you never have to parse ahead. You're just going to get the next field, get the next field. So basically, the bottom line is that each bytecode is self-defining in terms of length. If that helps.
Multiple records in a page. You have a table at the beginning.
Oh, absolutely. No.
Shows where the record boundaries are.
It has
You just scan the whole page because CPU is cheap.
Without going through the details of the on-disk structure, when you get down to a data page, it's a very classical structure used by just about every database system since IDMS, and that is either at the front or the back. It has a page line index, which is indexed by line number, and that gives you the offset and length of the record on the page. And the actual data storage doesn't know anything about record format. It only knows about, here's a record. It's opaque GOOK of n bytes long, and you store it and it gives it back. And it's a higher level who figures out what it means.
But the record is a sequence of fields.
The record is a sequence of fields.
Okay.
Yes.
So 2 questions. One, is Falcon available in production for MySQL? And then 2 is, I know you said we shouldn't really address this at the beginning, but why would or wouldn't I use this versus an ODB for a web application?
No, and its intrinsic goodness. Okay. The MySQL idea of talking about dates, and I was at DEC, it was a long time ago, but I was at DEC, where you get shot if you talked about dates. We are hoping to release the first alpha late July, early August. If I don't get done when it's supposed to get done, it may be September. But we're shooting for, and that's distinctly an alpha version. Depending, and beta in the fall, and we'll see how it goes during beta. We're hoping to have general availability in Q1 of next year. But it depends on how the beta goes. Why you would want to use this than InnoDB? We'll see what the final numbers turn out to be performance. I suspect frankly, they'll be comparable. One will probably be faster for summer operations, some will probably be slower for other operations. InnoDB has had more time to mature in the MySQL environment. There are impedance mismatches between the way Falcon does things and the way MySQL Server does things that from time to time slow it down. There are a lot of things that that can be optimized in the Falcon, internally in Falcon, that aren't yet optimized in MySQL. My plan, from my perspective, is it would be more flexible for a web application and better performing. It will make it much easier to give consistent application programming. I think it has an easier to use concurrency model for doing concurrent access. I think, certainly my goal is that for a web type application with high volume queries, that it should be substantially faster, but we'll see. I mean, I've been fairly impressed with the comparative performance of InnoDB. So, 6 months ago saying we'll beat it hands down, across the board. I'm not going to make that statement.
Yes.
Hands down across the board, yes. Mix the metaphor. Caught with pants down, right. So we'll see. But it is certainly targeted for web type applications. And lightweight as possible, flexible as possible, and sensitive to tuning. Simple, we don't have any performance quirks. Its recovery is virtually instantaneous under all conditions. Not always successful yet, but it's very quick.
Well, if it's gonna die on me, I want to know soon.
Yes.
Are you programming this all by yourself, or you have a team, or what?
We have a team. I'm doing most of the work right now. This is like this is a very high priority project within MySQL. Basically, I mean, everybody knows that Oracle bought InnoDB. That's very old news. The reaction inside of MySQL was kind of like they were shown the instruments, and they very much want to know that they have everything they need across the full pond spectrum. They have control of their own destiny, rather than dependent on Oracle's goodwill. I don't believe I said that. So when you want to get something done in a hurry, there's only one way to do it, and that is to have the fewest number possible doing it. So I've got a big support team. I've got QA people, and I've got performance measurement people, and I've got somebody running interference for me, and I've got my database theorist over here to take on theological arguments. And but at the moment, I'm doing the brunt of the coding. That will change as soon as it gets to beta, and I will be able to relax a little bit more. Yes?
Can you comment on the level of effort it was to integrate with MySQL? Was it easy? Was it hard? How much time?
Somewhere between hard and really, really hard.
So it's a man year, 5 man years?
Oh, no. Well, it'll end up being about 3/4 of a gym year. And a very, very intense gym year it has been. The initial part was fairly simple. All of the subtleties and the gotchas are enough to drive you absolutely berserk. Writing a storage engine, no matter what Brian says, is a really hard thing to do. And the hardest thing about it is it's not written down anywhere. Yes?
So you didn't have access to their pluggable architecture that they've been talking about?
Oh, yeah.
You did, and it was still hard even with that.
Oh, yeah.
It's late. We're starting from the existing engine that had assumptions. I know what you mean by impedance mismatch, but that's an EE term, not a DBA term.
Good, you can explain it, please.
It's understandable. When the highway goes from 4 lanes to 3 lanes, or 3 lanes to 4 lanes, the cars move around and everybody slows down, even though there are now more lanes. That's an impedance mismatch. His road is a perfectly good road, MySQL is a perfectly good road, but the dotted lines don't line up. He's got to line up the dotted lines in a way that causes the least pain to everybody.
Except himself.
Exactly.
Drive around Boston, exactly. Drive around Boston. There are a lot of places where the dotted lines don't meet up.
Yeah, and then there are little things, I guess, last week's big surprise is update, ignore.
Update, insert, delete, ignore.
Right, it says, do the operation, and if it doesn't work, don't worry about it.
It's not quite visible.
No, I didn't know that was there. A more insightful person than I am would have sat down and read the documentation front to back. Probably
Military carry.
before he accepted a fixed price contract to do a prototype. That's okay. They bought me before the prototype was done, so